Okay, so let's try to apply the congruences on the following problems. Okay, starting here first with number 1, find the unit digit of 3 raised to 103. Okay, so now, if we're going to look at this, it's quite hard to express that 3 raised to 103, right? So, we can't identify it easily. But with the use of modular arithmetic, let's try to uh, solve, okay, for the unit digit of this number. Okay, so let's say, let's observe. Okay, let's observe first when we raise 3 to a number. So let's say 3 raised to n, and let's try to represent that as 3 raised to 1, 3 raised to 2, 3 raised to 3, and 3 raised to 4, and last one 3 raised to 5. Okay, so starting with 3 raised to 1. Obviously, the unit digit there is 3, right? And also, let's say 3 raised to 2. So, 3 raised to 2 is equal to 9. Right? So, 3 raised to 2 is equal to 9. And then the next one, if we raise 3 to 3, so 3 raised to 3, that's 27. And the unit digit there is 7. Right? And then next one is 3 raised to 4, so that's 81. So that is, the unit digit there is 1. And then if we have 3 raised to 5, and that is 243, so we have the unit digit there of 3. And if we're going to continue the process here, let's say we have that 3 raised to 6, that's 729, we'll have that unit digit of 9. 3 raised to 7, that's 2187, so that's 7. So as you can see, there's a pattern that we can observe here. Right? There's a pattern that we can observe here. So we have that 3, and then the next one is 9, then the next one is 7, and then 1. And then we're going back to 3, okay? And then it's going to repeat. Okay, so if we're going to use that, if we're going to utilize that, uh, as you can see, let's try to uh, have that using the cyclic method. Okay, but now let's try to utilize, let's say that 3 raised to 4. Okay, that 3 raised to 4, we have that unit digit of 1. Okay, so how do we represent this using a congruence? Okay, we can represent this by having modulo 10. Okay, so having modulo 10, syempre, when we divide that by that number to 10, obviously the resulting remainder should be from 0 to 9 only. Okay, so that's why we can obtain the unit digit there. Okay, if we're going to use m as 10. Okay, so here we have 3 raised to 103 uh, is congruent to r modulo 10. Okay, so what is the remainder when we have 3 raised to 103 and we divide it by 10? Okay, so again, let's utilize that 3 raised to 4. Okay, so if we have that 3 raised to 4, we have the remainder of 1, right? Because that's 3 raised to 4, 81. So that's remainder of 1. Okay, then also let's try to use some properties of congruences from our previous discussion. So let's say we raise both 3 raised to 4 and 1 by 25. So if we raise both by 25, so we'll have 3 raised to 4 times 25. So that's 100, right? And then 1 raised to 25, that's 1. Okay, so we have 3 raised to 100 congruent to 1 modulo 10. Okay? So we are near. We're just going to have that another 3 for our exponent. So let's say we multiply that 3 raised to 100 by 3 raised to 3. Okay, so if we're going to multiply 3 raised to 100 by 3 raised to 3, also we should multiply 1 by 3 raised to 3. Okay, so this is one of the properties that we have from the previous video. Okay, So if we're going to simplify this, we have that 3 raised to 1 over 3, 27 modulo 10. Okay, but again, since we are after with the remainder when we divide it by 10, so that's 27, it can be simplified as remainder of 7, right? Because 27, you divide it by 10, you'll have the remainder of 7. Okay, so 3 raised to 1 over 3 is congruent to 7 modulo 10. So therefore, the unit digit here of 3 raised to 1 over 3 is 7. Okay? So let's try to solve another problem. Find the last digit of 19 raised to 205. Okay, so still, we're going to identify the last digit. Okay, so let's solve this. Okay, so notice that if we have 19, okay, raised to 205, and we're going to identify the last digit, we're going to divide it by 10. Okay, so we have here 19 raised to 205 is congruent to r modulo 10. Okay, so let's observe. Let's start first with 19. Okay, so if we divide 19 by 10, we have a remainder of 9. Okay, so 19 is congruent to 9 modulo 10. Okay, so let's say we look at that 9. Okay, let's focus to that 9. Okay, when we raise it by a number, let's observe what will happen. Okay, so let's say we have that as 9 raised to n. And let's try to, again, substitute some values. So let's say if we have 9 raised to 1, so that's 1, 9 rather. And then we have 9 raised to 2, that's 81, right? So 81, we have the last digit of 1. And then if we're going to have that 9 raised to 3, that is 729. Okay, 729. So the last digit there is 9. Okay, and then we have 9 raised to 4. That is 6,561. Okay, so if we're going to identify the last digit, that is 1. Okay, and then if we're going to continue this process, we'll have that 9 raised to 5. The last digit of that is 9. Okay, and also if we have that 9 raised to 6, we're going to have the last digit of 1. So as you observe here, if we have an odd exponent, the last digit is 9. Right? The last digit here is 9. But if we have an even exponent, the unit digit or the last digit here is 1. Right? So let's say we raise that 19 to 205 and we raise 9 by 205. And by our observation, as you can see, since we raise it with the odd number, obviously the last digit there is 9. Right? If we raise 9 to 205, the last digit there is 9. Okay, so if that's the case, we have our answer, right? So therefore, we have the last digit of 19 raised to 205, which is 9. Okay, that is 9. Okay? Okay, so let's try to solve another problem. Find the least digit non-negative residue when 2 raised to 16 is divided by 17. So this time, we're not going to identify the last digit or the unit digit, but we're going to solve for the least non-negative residue when we divide the 2 raised to 16 by 17. Okay, so let's say we have this 2 raised to 16 is congruent to r modulo 17. We don't know the residue. Okay, but let's try to observe. Okay, so if we have that 2 raised to 1, so obviously we have that 2. When we divide it by 17, we'll have the remainder of 2. 2 raised to 2, that's 4. So we'll have the remainder of 4. 2 raised to 3, that's 8. We'll have the remainder of 8. And then let's try 2 raised to 4. Okay, which is 16. So we'll have that remainder of 16. So 2 raised to 4 is congruent to 16 modulo 17. Okay, so One strategy that we can use here is to utilize the negative residue of this one. Okay, that's 2 raised to 4 is congruent to 16 modulo 17. So all we need to do is to subtract that 17 okay, to 16. So 16 minus 17 is negative 1. Okay, still, this is true. Okay, this one is true. Okay, so 2 raised to 4 is congruent to negative 1 modulo 17. Okay, so we identify the negative residue. Okay, now, let's try to raise both sides by 2 raised to 4 and negative 1 both by 4. Okay, so that's 2 raised to 4 and times 4 and then negative 1 raised to 4. Okay, 2 raised to 4 times 4 is 16. So 2 raised to 16 and then negative 1 raised to 4. So if we have this, negative 1 times negative 1 times negative 1 times negative 1, that is 1. Okay, so that's 2 raised to 16 is congruent to 1 modulo 17. So therefore, the least non-negative, since we are after with the least non-negative residue, when 2 raised to 16 is divided by 17, then we'll have that as 1. I will have that as 1. Okay? Now, let's try to apply some theorems on the following examples. The next examples that we will discuss. Okay, starting first with Fermat's little theorem. Okay, Fermat's little theorem. We're in. Let's say we have our observation that we let P as prime number. So if GCD of A and P is 1, then we can say that this is true. Okay, so we have here A raised to P is congruent to A modulo P. And also it's true that if we have that A raised to P minus 1 is congruent to 1 modulo P. Okay, this is true provided, again, that the GCD of A and the prime number is 1. Okay, so let's try to utilize this. Let's try to use this. Okay, so take note of this congruences. Okay, so let's try to evaluate what is our residue. So when we have 2 raised to 25 modulo 23. Okay, 2 raised to 25 modulo 23. So as you can see here, we have 23 as prime. Okay, so 23 is prime number. So that's 1. Okay, one of the requirement. And then another one, we have A as 2. Okay, our A here is 2. And again, our prime number is 23. And the GCD of 2 and 23 is obviously 1. Okay, it's obviously 1. So therefore, we can utilize this theorem. Okay, so if that's the case, we have this one. So let's try to substitute. So we have that 2 raised to 23 minus 1, that's 22, is congruent to 1 modulo 23. Okay, so 2 raised to 22 congruent to 1 modulo 23. So we're near to our given. So let's say we multiply it by 2 raised to 3. Okay, let's multiply that to 2 raised to 3. So if we're going to multiply that to 2 raised to 22, we're going to multiply it also with 1. Okay, so 2 raised to 22 times 2 raised to 3, that's 2 raised to 25. And then 2 raised to 3, again, that's 8. So 8 times 1 is 8. So therefore, we have our residue of 8. So 2 raised to 25 is congruent to 8 modulo 23. Let's have another example. So let's say we have here 3 raised to 1001 modulo 5. Okay, 3 raised to 1001 modulo 5. Let's identify the remainder. Okay, so let's say we have the GCD again of our prime number, which is 5, and our A here is 3. Okay, so the GCD of 3 and 5 is 1. Okay, so therefore, we can use the Fermat's little theorem. Okay, it's true. So we have that 3 raised to 5 minus 1, so 3 raised to 4 is 1 modulo 5. Okay, so we have here 3 raised to 4, but we need to have that 3 raised to 1001. So let's say we raise both 3 raised to 4 and 1 by 250. Okay, so 3 raised to 4 times 250 and then 1 raised to 250. Okay, and that is 1 raised to 250, that's 1. Okay, and then we have 3 raised to 1000. Okay, so 3 raised to 1000 is congruent to 1 modulo 5. Okay, but in our problem, we need to have that 3 raised to 1001. So that's why we need to multiply 3. Okay, we need to multiply 3. So that's 3 raised to 1000 times 3 is congruent to 1 times 3 modulo 5. And then if we're going to simplify that, we have 3 raised to 1001 congruent to 3 modulo 5. So we have here our residue, our remainder of 3. Okay, let's have the next one. Okay, let's have example number 6. Okay, so let's try to evaluate 15 raised to 601 plus 7 modulo 101. Okay, modulo 101. So again, let's verify. Let's check. Let's start first with here 15 raised to 601. Okay. Disregard first that 7. And let's focus here with 15 raised to 601 and then modulo 101. Okay. So as you can see here, we have 15 as our A and our P here is 101. So 101, 101 is a prime number. So given that, we have the GCD of 15 and 101 is 1. Okay, so if that's the case, we can apply the Fermat's little theorem. Okay, so we have here 15 raised to 101 minus 1, so that's 15 raised to 100 is congruent to 1 modulo to 101. Okay, and then since we need 601, let's say we raise it by 6. Okay, so 15 raised to 100 raised to 6 is congruent to 1 raised to 6 modulo 101. Okay, so if that's the case, we have 1 raised to 6, still 1. So 15 raised to 600 is congruent to 1 modulo 101. Okay, but again, we need 601. So let's multiply both by 15. So we have 15 raised to 600 times 15 is congruent to 1 times 15 modulo 101. Okay, and that is 15 raised to 601 congruent to 15 modulo 101. Okay, then the last one, since we need to add that 7, okay, we need to add that 7 here. So let's say we add 7. So this is still true using the properties. Okay, if we add both by 7, so we'll have 15 plus 7, that's 22. So therefore, 15 raised to 601 plus 7 is congruent to 22 modulo 101. Okay, so we have the residue here of 22. Okay, so aside from the Fermat's little theorem, let's try to utilize Euler's theorem. Okay, so here we have Euler's theorem, wherein we have, or we let the GCD of A and N as 1. Then we can have here as A raised to N is congruent to 1 modulo M. Okay? Where N is equal to P sub 1 times P sub 1 raised to N sub 1 times P sub 2 raised to N sub 2, and then multiplied by up until P sub M raised to N sub M. Okay? And this is true that we have that Euler's here that phi of n is equal to n times the quantity of 1 minus 1 over p sub 1 times the quantity of 1 minus 1 over p sub 2 up until 1 minus 1 over p sub m. Okay, so here actually we're going to identify the prime factorization. Okay, we're going to identify the prime factorization here so that we can have that p sub 1, p sub 2 up until p sub m. Okay, so p of n is the number of positive integers less than n, wherein it is relatively prime to n. Okay, so we're going to identify the prime factorization here. Okay, but we're going to get the factors. Okay, just the prime factors. Okay, so let's have an example. Okay, let's have an example. Let's say we have here 15 raised to 100 modulo 34. Okay, here we have that 34, and then we're going to identify the factors. So 34 is 2 times 17. Okay, so we have here phi of 34 is equal to that 34 times the quantity of 1 minus 1 over one of the prime factors, 2, times the quantity of 1 minus 1 over 17. Okay, and if we're going to solve this, 34 times the quantity of 1 minus 1 half times the quantity of 1 minus 1 over 17, that is 16. Okay, then based on its theorem, we're going to utilize that 16 as our exponent. Okay, so we'll have that 15 raised to 16 is congruent to 1 modulo 34. Okay, so this is true. Okay, so the value that we will get here will become our exponent. Okay, so 15 is raised to 16 is congruent to 1 modulo 34. Okay, but still, we need to have that 15 raised to 100. So we know for a fact that 15 raised to 16, when we divide it by 34, the remainder is 1. But again, we need to have that 15 raised to 100. Okay, so let's say we raise it by 6. Okay, we raise it by 6. So 15 raised to 16 times 6, and then we have that 1 raised to 6. Okay, and then with that, 1 raised to 6 still 1. Okay, so 15 raised to 96 is congruent to 1 modulo 34. Okay, and then here, we need to have another 4, 15 raised to 4. So let's multiply both sides by 15 raised to 4. Okay, so in this case, 15 raised to 4 is tolerable. We can identify its value. 15 raised to 4 is 50,625. Okay, 15 raised to 4 is 50,625. Okay, then if we're going to solve that, 50,625, and we divide it by 34, we'll have the remainder of 33. Okay, we'll have the remainder of 33. Okay, so again, 15 raised to 4 is 50,625. Okay, so 15 raised to 4 is 50,625. And if we divide that by 34, we'll obtain the remainder of 33. So therefore, we'll have this 15 raised to 100 is congruent to 33 modulo 34. Okay? Let's have another example. Okay, so let's try to evaluate 3 raised to 2003 modulo 25. Okay, 3 raised to 2003 modulo 25. And then let's have the prime factorization of 25. That is 5 squared. Okay, that's 5 squared. So here, the prime factors, there's only one, right? There's only one, which is 5. So therefore, we don't need to repeat that. Okay, we don't need to repeat that. Just get the one, okay, which is 5. So with that, we'll have the 25 times the quantity of 1 minus 1 over 5. Okay, so again, no need to repeat this 1 minus 1 over 5. Okay, just 1. Okay, so 25 times the quantity of 1 minus 1 over 5. And if we're going to simplify that, that is 20. Okay, and then we can use that again as our exponent. So we'll have that 3 raised to 20 is congruent to 1 modulo 25. Okay, 3 raised to 20 is congruent to 1 modulo 25. Okay? And then, since we need 2003 here as our exponent, let's say we raise both by 100. So 3 raised to 20 raised to 100, and then 1 raised to 100 is 1. Okay, so we have 3 raised to 2000 is congruent to 1 modulo 25. Okay, so we only need that 3 raised to 3. So we multiply both by 3 raised to 3. Okay, 3 raised to 3 is 27, right? And 27 divided by 25 will have the remainder of 2. Okay, so therefore we have 3 raised to 2003 is congruent to 2 modulo 25. Okay, so the residue here is 2. Okay? Next one. Okay, find the last two digit of 3 raised to 250. Find the last two digit of 3 raised to 250. Okay, so here we're going to identify what should be the value that we will divide to 3 raised to 250 to get that two digits. So if we're going to identify the unit digit or the last digit, we divide it by 10. Okay, but if we're going to identify the last two digits, we're going to divide it by 100. Okay, we divide it by 100. Okay, so let's say we have that 100. So we have the prime factorization of 2 raised to 2 times 5 squared. Okay, and then again, the exponent does not vary here, so we're going to use the prime factors only. Okay, so we have here 100 times the quantity of 1 minus 1 half times the quantity of 1 minus 1 fifth. Okay, and if we're going to simplify that, that is 40. Okay, that is 40. Okay, so we're going to utilize that 40 as our exponent. So that's 3 raised to 40. Okay, so 3 raised to 40 is congruent to 1 modulo 100. Since we need 250 as our exponent here, let's say we raise it by 6. So 3 raised to 40 raised to 6 is congruent to 1 raised to 6 modulo 100. Okay, and 1 raised to 6, that's 1. So 3 raised to 240. Okay, 3 raised to 240 is congruent to 1 modulo 10. Okay, and then since we are after with 250, we're going to multiply 3 raised to 10. Okay, we're going to multiply 3 raised to 10. Okay, so if we're going to multiply 3 raised to 10 here, we'll have 3 raised to 10 as tolerable. So we're going, we can solve this as 59,049. Okay, that's 59,049. Okay, so if we divide 59,049 by 100, we'll have 49. Okay, as our quotient. The remainder rather. So 3 raised to 250 is congruent to 49 modulo 100. So therefore, the last two digits of this number 3 raised to 250 is 49. Okay, so remember again, if you're going to identify the last two digits, use 100. Okay, divide it by 100. Okay? Okay, so let's try to have the last theorem. Okay, let's try to have the last theorem. But let's just go back to one of the questions during your quiz B in our math days, right? On our math week. So let's try to solve this. Find the remainder when 1 factorial plus 2 factorial plus 3 factorial plus up until 99 factorial plus 100 factorial is divisible by 12. Okay, so our next theorem, it has something to do with the factorial. Okay, but let's try to solve this. Okay, so in order to solve this, we should recognize all the values here from 1 factorial up until 100 factorial if it is divisible by 12. So let's say we have 1 factorial, so it's not divisible by 12, obviously, because that's 1. 2 factorial still is not divisible by 12. And then 3 factorial still, 3 times 2 times 1, that's 6 only. But if we're going to continue the process, let's say 4 factorial, so we have that 4 times 3 times 2 times 1. So obviously we have 4 times 3. Okay, so it's divisible by 12. And if we're going to continue the process up until 5 factorial, 6 factorial, up until 100 factorial, there's a 4 times 3 there. Right? There's 12 there. So therefore, if we're going to add that, 4 factorial plus 5 factorial plus 6 factorial up until 100 factorial, it is divisible by 12. Right? It's divisible by 12. So therefore, we can deduce that. Okay? We can remove that 4 factorial up until 100 factorial and simplify that 1 factorial plus 2 factorial plus 3 factorial. Okay, and 1 factorial is 1, 2 factorial is 2, and 3 factorial is 6. So we're just going to add that. 1 plus 2 plus 6 is 9. So therefore, the remainder when we have 1 factorial plus 2 factorial plus 3 factorial up until plus 100 factorial is divisible by 12, then we have the remainder of 9. Okay, we have the remainder of 9 here. Okay? So now, let's try to solve some problems with regards to that factorial. Let's try to relate some concepts of congruences, specifically when it comes to Wilson's theorem. When it comes to Wilson's theorem. So let's say, let P be a prime. Okay, then we can have this. P minus 1 factorial is congruent to negative 1 modulo P. Okay, so the residue here is negative 1. So P minus 1 factorial is congruent to negative 1 modulo P. Okay? So let's try to solve some problems. Okay, what is the remainder when 10 factorial is divided by 11? Okay, so as you can see here, our P here is 11. So obviously that's 11, right? So let's have another method first before we proceed with Wilson's theorem. Okay, let's expand this. Okay, let's say that 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, and let's regroup this. Okay, let's try to regroup this in order for us to have that remainder that when we divide that 2, the product of that 2 is 1. Okay, so let's regroup that as 2 times 6, 3 times 4, 5 times 9, 7 times 8. Okay, times 10. Okay, so let's try to have this. So as you can see, 2 times 6 is 12, 3 times 4 is 12, and 5 times 9 is 45, 7 times 8 is 56. Okay, so what will be the remainder? Okay, what will be the remainder if we divide all of this by 11? Okay, so let's say 2 times 6 is 12. 12 divided by 11, we have the remainder of 1. Right? We have the remainder of 1. 3 times 4 still 12 divided by 11, we have the remainder of 1. 5 times 9 is 45. When we divide that by 11, and that's still, we have the remainder of 1. 7 times 8 is 56. If we divide it by 11, we'll have the remainder of 1. So therefore, we'll have this. Okay, we can express that as this. 10 factorial is congruent to 1 times 1 times 1 times 1 times 10 modulo 11. Okay, and then if we're going to simplify that, okay, we have 10. Okay, 10 factorial is congruent to 10 modulo 11. Okay, but if we're going to have its negative residue, so 10 minus 11, that's negative 1. Okay, so that's 10 factorial is congruent to negative 1 modulo 11, which is true if we're going to utilize the Wilson's theorem. Right, so provided that our P here is 11. Okay, it's prime, so 11. So 11 minus 1, that's 10 factorial. Okay, and 10 factorial is congruent to negative 1 modulo 11. So it's true. Right, so it's true. Okay, let's have another example. Okay, so for you to understand the concept of Wilson's theorem. Okay, so here again, what is the remainder when 18 factorial is divided by 19? Okay, if we divide it by 19. So again, let's try to express it, that 18 factorial. Let's expand this. Okay, 18 times 17 up until times 1. Okay, and then let's again have its pair. Okay, wherein when we divide that product of the two numbers, when we divide it by 19, the result is either 1 or negative 1. Okay, so let's say we regroup that as this one. Okay, so 18 times 1 times 17 times 9 times 16 times 6 times 15 times 5, 14 times 4, 13 times 3, 12 times 8, 11 times 7, and 10 times 2. Okay, 10 times 2. Okay, so let's say we have that 18 times 1 Okay, 18 times 1 is obviously 18. And if we divide it by 19, we'll have the remainder of 18. But if we're going to extend it, we'll have the negative value, residue. We'll have that negative 1, right? Negative 1. And then we have that 17 times 9. 17 times 9 is 153. So if we're going to divide it by 19, we'll have the residue of 1. Okay, so 153, that's divided by 19. So that's for the remainder of 1. Okay, and then also when it comes to 16 times 6, okay, 16 times 6, that's 96. And then if we divide it by 19, we'll still have a remainder of 1. Okay, and if we continue the process, so here we have remainder of negative 1. 17 times 9, we have 1. 16 times 6, we have 1. 15 times 5, we'll have negative 1 as our remainder. 14 times 4 is negative 1. 13 times 3 is 1. Okay, so if we divide the 13 times 3, that's 39. Divided by 19, we'll have that as 1. Okay, and then 12 times 8, and then 11 times 7, 10 times 2. Still will have the remainder of 1. Okay? So if we're going to simplify this, negative 1 times 1 times 1 times negative 1 times negative 1 times 1 times 1 times 1 times 1, that is negative 1. Okay, so 18 factorial is congruent to negative 1 modulo 19. It should be 19, correction. Okay, so that is 19. Okay, it should be 19. Okay? And then, if we're going to apply, okay, if we're going to apply the Wilson's theorem here, we'll have this. Okay? So 19 is our remainder. So is our p rather. So 19 minus 1, that's 18 factorial. So 18 factorial is congruent to negative 1 modulo 19. Okay, if we're going to find the least non-negative residue, all we need to do is to add that 19 to negative 1. So negative 1 plus 19, that is 18. So this is the least non-negative residue. Okay? Let's have another example. Find the remainder when 15 factorial is divided by 17. Okay, so let's have this 17 is prime. So obviously we can utilize the Wilson's theorem. Okay, but the problem here is if we have 50 minus 1, so 17 minus 1, that's 16 factorial. Right? That's 16 factorial. But we need 15 factorial here. Right? We need 15 factorial here. So let's rewrite this 16 factorial as 16 times 15 factorial. Right? 16 times 15 factorial. And then that negative 1, let's just add that 17 to have that non-negative residue. So that's 16. So we have 16 times 15 factorial is congruent to 16 modulo 17. So take note again, 16 factorial can be expressed as 16 times 15 factorial, right? And then remember, we have our property that if we're going to have the cancellation property, so let's check. We have 16 as our C and our M here is 17. So we have the GCD of 1. So if we divide this all by 16, we'll have 15 factorial. 16 divided by 16 is 1. And then 17 divided by that GCD of 1, which is 17 still. So 15 factorial is congruent to 1 modulo 17. Let's have the last example. Okay, so let's have the last example here. Find the remainder when 4 times 29 factorial plus 5 factorial is divided by 31. Okay, so 4 factorial, 4 times 29 factorial plus 5 factorial is divided by 31. Okay, so recall that we have here 31. So therefore, we can still use the Wilson's theorem here, wherein P is 31. So 31 minus 1 is 30. So 30 factorial is congruent to negative 1 modulo 31. Okay, and then if we're going to identify the least non-negative residue for this is, we're going to add that 31. So negative 1 plus 31, that's 30. So we have that 30 factorial is congruent to 30 modulo 31. Okay, but again, the problem here is we have 29 factorial. Right, we have 29 factorial here. So we need to produce 29 factorial here. Okay, so let's just go back. Let's say 30. So if we divide 30 by 31, we'll have negative residue of negative 1. Right? So 30 divided by 31, so that's 30. But if we're going to find the negative residue of that, that's negative 1. Right? So that's negative 1. And then we don't know the 29 factorial. So let's say we represent that as R. Okay, let's represent that as R. Okay, then let's say we multiply this. Okay, using again another property. So let's try to multiply this. So 30 times 29 factorial and then negative 1 times R. Okay, so we'll have that 30 times 29 factorial is congruent to negative 1 R modulo 31. Okay, simply 30 factorial is congruent to negative 1 R modulo 31. Okay, so notice that this one and then this one is the same, right? It's the same. So we can identify the value of R here. So when we equate that negative 1 to negative 1 minus R. So negative 1 minus R is equal to negative 1. So let's divide both sides by negative 1. And our R here is 1. So we can substitute now here, right, for the 29 factorial. Okay, so we can say that the residue, okay, of the 29 factorial, when you divide it by 31, that's 1. Right? So 29 factorial is congruent to 1 modulo 31. Okay, then we can now solve this. Okay, let's say we multiply it by 4. Okay, so multiply it by 4. So 4 times 29 factorial is congruent to 4 times 1 modulo 31. So that's 4. Still 4. Okay, but again, we need to add that 5 factorial. Okay, we need to add that 5 factorial. So let's say we add both by 5 factorial. So if we're going to add both by 5 factorial, so we'll have here 4 plus 5 factorial. Okay, and 5 factorial is 5 times 4 times 3 times 2 times 1, and that is 120. Right, so 120. And if this is 120, okay, 120 plus 4 is 124. Okay, so 124, let's divide it by 31. Okay, 124 divided by 31 is 4. And we don't have a remainder. Okay, we don't have a remainder. So therefore, we can say that 124 divided by 31, we have the remainder of 0. So therefore, when we divide 4 times 29 factorial plus 5 factorial by 31, the remainder is 0. Okay, the remainder is 0. Okay? So now you can try this. You can try this and then let's try to solve this. Okay, let's check your output by next meeting. Okay?